everybody to experiment FM2. This is pretty exciting stuff, I think. It's pretty low speed, but it's exciting, and we're going to be looking at the flow over an airfoil and approaching it from measuring forces on the body. That's this wind tunnel here. I'll tell you about LVDTs in a minute. And then also we're going to be measuring the pressure distribution around an airfoil. And then in the further of these 3 wind tunnels, 3 little mini wind tunnels, the last one we're going to be doing flow visualization using the smoke quiet technique, and again with the airfoil. The airfoil that we've got is called a NACA, N-A-C-A 0012, and the 00 tells you that there's no what the hell is it called when the airfoil is
no camber.
Camber, yeah. Thank you very much.
It's symmetric.
Sorry about that, everybody. It's a symmetric airfoil, so the shape on the top is the same as the shape underneath. And it's, for some reason, it sort of got everybody's imagination. And so any paper that's at all to do with low Reynolds number airfoils, people choose this NACA 0012. It just works really well. So I think I'm just going to tell you a little bit about this wind tunnel. And then we'll go from there. So this wind tunnel has a pitot-static tube up here, so you can measure the velocity of the flow using that, using Bernoulli's equation and the pitot-static tube. And so we measure the pressure using this transducer here, and to get our force on the body, just the airfoil in here, this thing here, to get the force of the fluid on the airfoil, we've got the airfoil suspended by a sting, which is a long kind of rod that's underneath this black thing here. The black thing is just to not allow the wind to blow against the sting, which is the vertical rod that's holding our airfoil. If it was allowed to push against the sting inside here, then you get completely fallacious results. It wouldn't be worth anything. So we've covered that up, and I think we can see if you press down on the airfoil quite lightly, you can see these numbers changing. Anytime it's something like that, it's really fantastic, because when you're troubleshooting, invariably you push on the thing and nothing happens. So it's always exciting to know that something is working in the world.
Okay, thank you, Skipper, for that wonderful introduction to the first part of the lab. So we're going to start off by turning the wind tunnel on. And so to do so, I'm going to flip this switch right here to on.
Okay, and now we're going to come to the control panel, make sure it's set to 14 Hertz, and click run. With a lovely musical introduction. So we're going to start on this page in your lab handout with the force measurements. And as you can see, we're going to be going through a range of angles of attack of the airfoil. And as we do this, we're going to measure the lift in volts, the drag in volts, and the dynamic pressure, which you remember from the first lab, the dynamic pressure is equal to PT minus PS, which we'll measure from our pitot-static tube. Using this data, we can then find the coefficient of lift and the coefficient of drag using the given equations. So we're going to start with our NACA 0012 airfoil at 0 degrees. And we're going to be measuring, firstly, the lift in volts, which, Jay, what is it?
Right now, it's 0.02.
And the drag?
Which is very close to 0. It's 0.008.
And our PT minus PS, we measure up the top here, which is
0.412.
Okay, so before we move on to 3 degrees, Jay, what did you notice about the lift for 0 degrees?
The lift was not 0, despite the airfoil having a 0 degree angle of attack.
And it's also a symmetric airfoil. Is that something we expect?
That's not something you'd expect with a symmetric airfoil.
So looking at this setup, why do you think we got a non-zero lift?
So looking at this setup, we can see that the airfoil is on a sting, and that breaks the symmetry of the airfoil. So you can see the top side is no longer symmetric to the bottom side when you include the sting, and that's causing the lift to no longer be zero anymore.
Excellent. So we're going to move up to 3 degrees angle of attack. And you can see on the front here, we've got a little silhouette of the airfoil, and we can move it up to 3 degrees using our little pointer here. So we reach in, and holding the airfoil from the leading edge, we can move it up. And Jay, am I?
A little bit more. A little bit more. A little bit more. Perfect.
All right, so we've moved our airfoil up to 3 degrees, and our lift voltage is now
0.052.
and our drag.
See, our drag is negative 0.006. We see that there's a negative value in front of the drag. Obviously, we're not creating negative drag, which is thrust in this case. That's just a matter of direction. So with our airfoil system, positive drag is defined as thrust in this case, and the negative drag is actual drag, so that's why there's a negative sign in front of the drag.
So when you're writing down your values here, you're just going to write down 0.006. Right, so what's our next angle?
PT minus PS is 0.418 for this case.
Yeah, go ahead of myself.
Yep. The next angle is 6 degrees.
Good. The lift?
So the lift has now increased to 0.080. Our drag has also increased now to 0.010.
And our PT minus PS?
Is at 0.415.
So our next angle is going to be 9 degrees. Okay, so we have our data sheet now. Jay, what are some things that you notice here?
So immediately right off the bat, I noticed that PT minus PS is decreasing as we increase our angle of attack.
So why do you think this is the case?
So I think that's probably because of blockage, which is something we talked about in FM1 tutorial. And if you want to demonstrate that, Sarah.
Yep. So if we have a look at PT minus PS right now, as you can see, it's lower than it was at the start because our airfoil is, there's more area towards the incoming flow. But if I was to then stand at the edge of the wind tunnel, what happens to PT minus PS?
It's decreasing even more now. So it was 0.296 without you standing there. It seems to be hovering around 0.22 or so with you there.
All right, so what else do we notice from our data sheet? What do you notice about the lift?
So we notice that the lift initially increases, then decreases again, and then increases at the end again.
Yep, and what about drag?
And drag seems to just steadily increase throughout the thing.
All right. So this seems to indicate to us that there are different regimes of flow.
Mm-hmm.
And if you have a look at your appendix, you can see that there are 4 different regimes here. Mm-hmm. So Jay, can you tell us about the 4 regimes and the angles that they're covering?
Yeah, so the 4 regimes of flow, as you can see in your appendix, are the first regime is attached flow, which occurs from about 0 degrees to 6 degrees.
And what's happening in there? The lift is increasing?
Right, so with attached flow, as you increase the angle of attack, you can increase lift without increasing drag very much. And in that flow, as the name suggests, the flow is entirely attached to the airfoil. There's no stall yet. As we increase our angle of attack from 6 degrees to 12 degrees, we enter this state called partial stall, which as we increase angle of attack, we get minor increases in lift and also minor increases in drag. At this stage, the airfoil has stalled, but hasn't fully stalled, so you'll see this later on in the lab, but the separation point moves from the trailing edge all the way up to the leading edge as you increase the angle of attack. And from 12 degrees to 20 degrees, we enter complete stall. So in this range, increasing the angle of attack no longer leads to an increase in lift. Instead, we're just increasing drag by increasing angle of attack. And finally, beyond 20 degrees, we're in what we call the flat plate flow. At this point, the airfoil, it's no longer important that the airfoil is shaped like an airfoil. What the flow sees is essentially a flat plate. And so increasing the angle of attack will increase the lift, but also significantly increase the drag.
Okay, so Jay, can you tell me a little bit more about how this partial stall regime works?
Right, so for attached flow, if we look at the flow of the airfoil, the flow itself stays attached from leading edge to trailing edge, so it does not detach from the body of the airfoil. But as we enter partial stall, we start getting separation. And so the separation starts at the trailing edge.
So it starts back here?
Right, and as we increase the angle of attack, the separation point slowly moves up towards the leading edge until we enter the complete stall regime at about 12 degrees or so when it's fully stalled. And so at full stall, the separation point occurs at the leading edge.
Excellent. Okay, so now we're moving on to our second experiment of the lab, which is measuring the pressure over a NACA 0012 airfoil again. So we're going to begin this lab by starting up our wind tunnel. It's already switched on, excellent. And again, moving to 14 hertz. Getting our lovely music to start it.
Melody.
Sorry?
It's a beautiful melody.
So you can see the instrumentation's a little bit different to the force balance experiment. So once again, we have a pitot-static tube at the front of the wind tunnel. And what's that going to measure for us?
That's going to measure the dynamic pressure.
Which is equal to?
PT minus PS.
PT minus PS. So then we notice there's a series of pressure taps coming out of the airfoil. So each of these correspond to a little hole on this top surface of the airfoil. And Jay, do you want to talk about what they are? X over C?
Yeah, so similar to FM1, each of these pressure tap locations corresponds to a certain location on the airfoil.
Yep.
So
What do we start with?
So we start with actually pressure tap location number 1, which is PT minus PS.
Yeah. So again, we're using the scanning valve to cycle through all our different pressure taps.
Mm-hmm.
So number 1 is our PT minus PS.
Right. Our second point is X over C of 0.03, so that is 3% of the way down the chord length.
Yep.
Third location is 10%, fourth location is 20%, and then it just increments by 10% to our 10th location, which is 80% of the way down the chord length.
So when I look at this data sheet, I notice that there's still 0.9 and 1. What do we do for that?
Right. So at that point, the airfoil is too thin to be drilling the pressure tap holes in. So we're going to extrapolate our data to the trailing edge at that point.
So what we're going to do is we're going to set X over C of 1.0 to have a pressure of 0, and at X over C of 0.9, the pressure is going to equal to half of what it was for 0.8. Okay, so if we have a look at our data sheet, we notice that there are a lot of different columns that we're going to be filling out. So we've already talked about the pressure taps and the different X over C locations, so we already know what those mean. As we alluded to before, we're going to be measuring our P minus PS values. So we're going to be measuring the pressure at each of these locations relative to PS. And this is going to be the value, do you want to lift it up for a second? Lift it up. It's going to be the value that's displayed here. And back down.
Gotcha.
So as we cycle through on our scanning valve, we're going to measure P minus PS, so PT minus PS and then 0.03 all the way to 1. And that's just going to be the values read out. Following this, we're going to be looking at P minus PS lower. Now, for 0 degrees, Jay, what does that mean?
So for 0 degrees, it should be symmetric on both the upper and lower surfaces. So we're just going to copy the values we measure from the upper surface to the lower surface.
Perfect. So the next column along is CPU. So this means the coefficient of pressure upper. If you recall from FM1, what's our definition of CP?
So CP is the pressure divided by the dynamic pressure.
So it's going to be P minus PS divided by?
What you measure from pressure tap location number 1, PT minus PS, which is your dynamic pressure.
Yeah, so CP upper is P minus PS upper divided by PT minus PS. And this is going to be the same for our coefficient of pressure lower. Alright, so our next column along is our delta CN. So CN stands for our normal coefficient, and how do we calculate that?
So all we're going to do to calculate that is subtract our coefficient of pressure from the lower face, or subtract our coefficient of pressure from the upper face from the coefficient of pressure of the lower face.
So CPL minus CPU. Our next column along is going to be delta Cm, and this stands for our moment coefficient. And the way that we calculate our moment coefficient is we take our delta Cn value and times it by our x over c. So next column along is our weighting function. So Jay, do you want to tell us about that?
Yeah, so what we've calculated is our Cn and Cm at each location, but we want to find the total Cn and Cm for the airfoil. So we're going to multiply the values we calculated at each location by the weighting function and sum it all up to get the total.
So we're going to do this both for our normal coefficient and our moment coefficient. Now if we look closer at the bottom here, we actually have the derivation of our normal coefficient, which comes out again as our summation of each normal coefficient times the weighting function, and same for the moment coefficient. So you're going to take your values from the normal coefficient and moment coefficient and get one value for each of them. From this, we can work out our coefficient of lift and coefficient of drag. So Jay, what does our coefficient of lift equal?
So our coefficient of lift is our normal coefficient multiplied by cosine of alpha, alpha being the angle of attack that the airfoil is set at. So for this case, alpha is 0 degrees.
And our coefficient of drag?
Is our normal coefficient multiplied by sine of alpha, again, alpha being 0 degrees for this case.
Excellent. Now the last thing that we have here is this x over c subscript capital C capital P, which is equal to Cm over Cn. What's this, Jay?
So this is our center of pressure, and this is the point on the airfoil at which there is no moment.
Exactly. So if I am standing on the airfoil at the center of pressure, it means that the moment is balanced either side of me. Okay, so we're starting with our airfoil at 0 degrees, and we're at pressure tap location number 1, which is PT minus PS. So P minus PS upper is
0.045.
I'll write it down.
Wait, sorry, 0.45, not 0.045.
Location number 2, which is x over c of 0.03, is equal to
Minus 0.098.
x over c of 0.1, P minus PS upper is equal to
Minus 0.169. Pressure tap location number 4 is minus 0.177. For number 5, it's minus 0.168. For 6, it's minus 0.151. For 7, it's minus 0.133. For 8, it's minus 0.116. For 9, it's minus 0.097. And for 10, it's minus 0.082.
Okay, so for x over c of 1.0, it's going to be 0. And for x over c of 0.9, it's going to be?
Minus 0.041. It's just, we're linearly extrapolating from pressure point number 10 to 0 at our trailing edge.
And our home button works. So now that we have our data for our airfoil at 0 degrees, we're actually going to compare the data that we obtained to data for a potential flow over a NACA 0012. So this is coming from this famous book, Theory of Wing Sections, which you can see we store directly above our wind tunnel. And this is in your appendix handout, which I can find the front cover for. So in your appendix handout, we have a copy of this for you. And you can see, we show you how to get this potential flow curve over our NACA 0012 at 0 degrees. So you can see it says from the previous data page, we've got CP equation, and we can extract that data. So we're inputting it into this equation directly from this third column. So at home, you can reconstruct this plot by yourself. Your CP is going to be equal to 1 minus this third column. And you can see you've got X as a percent of C for your location. So you're going to have negative CP and X over C. So something I'm going to point out right now, you might have noticed I said it's negative CP. So this is convention when we're plotting the pressure over airfoils. So make sure you're very careful when you're plotting at home that your y-axis is negative CP. Okay. So Jay has filled out our potential flow over a NACA 0012 airfoil compared to the actual results we got in our wind tunnel. So Jay, what do you notice about this plot?
So the first thing I noticed is that it actually follows the potential flow prediction very well. The only difference is that as we get closer and closer to the trailing edge, there seems to be some discrepancy.
Okay. So I think we should talk more about that, but I think we'll get another diagram for this.
Mm-hmm. Yeah.
So to explain this discrepancy, we're going to have a look at the difference between potential and real flow. So before we draw on some streamlines here, what are our assumptions for potential flow? Three I's.
Right. So the assumptions for the potential flow are, as Sarah said, 3 I's. So number 1 is the flow is irrotational.
Number 2?
Number 2, the flow is incompressible.
And number 3?
The flow is inviscid.
Excellent. So what does the flow look like?
So with potential flow, we have our incoming flow that creates a stagnation point here. And at the trailing edge, we also have a stagnation point leading out. And the flow stays attached to the airflow throughout the entirety of it. So it follows the shape of the airfoil perfectly as it travels around the airfoil.
So what we're going to have a look at now is this assumption that the flow is inviscid. Is that flow inviscid in the real flow?
No, it is not inviscid in the real flow.
So what implication is that going to have? What's going to form around our airfoil?
So in the real flow, a boundary layer will form around the airfoil.
Exactly. So if we have a boundary layer, do you want to maybe draw our boundary layer?
So the boundary layer starts to develop at the leading edge, and it gets larger and larger as we approach the trailing edge.
So shading in our boundary layer now. So our streamlines, draw them in, are now going to...
Because we have this boundary layer, they're actually going to follow
the shape of the boundary layer.
Right, instead of the shape of the airfoil. And so now the streamlines are following a shape that's very close to a NACA 0012, but not quite exactly the shape of a NACA 0012 due to the boundary layer.
Yeah. And so because we know the pressure does not change in Y across a boundary layer, so whatever the pressure is here is going to be equal to the pressure here, because there's no change in pressure in Y across the boundary layer. So instead, what we're going to be measuring is the pressure at the edge of this boundary layer. So what we're going to be measuring in the end here is going to be the shape of the airfoil plus the boundary layer. Do you want to add any more to that?
And that explains why the values we measured for pressure are very close to what we saw with the potential flow, because for the most part it is very close to the shape of the airfoil. But as we get closer and closer to the trailing edge, it diverges a little bit due to this boundary layer getting thicker as we travel downstream from the leading edge.
So as you can see in your lab handout, we're now going to be looking at the pressure over the airfoil at 3 degrees. So Jay, do you want to jump into the frame with me? Excellent jumping. So firstly, we're going to put our airfoil up to 3 degrees. And this is now attached to it, so it's much easier than the previous experiment. So as we said at the start here, our pressure taps are along the top surface. So it's going to be easy for us to get P minus PS upper. We don't have any pressure taps on the lower surface, Jay, so how do you think we're going to get our P minus PS lower?
So because the airfoil is symmetric, we can just go to -3 degrees to get the lower face.
Exactly. So we're going to go through it twice. We're going to go through it once to get P minus PS upper, and then we're going to put it to -3 degrees to get P minus PS lower. So starting on the upper surface, pressure tap location number 1, PT minus PS is equal to?
That's the dynamic pressure.
Which is equal to?
0.45.
So to do the lower surface, we are now going to move our airfoil, I don't need to do that, to -3 degrees. Okay, so we're going to start with location number 1, which is PT minus PS.
And that is 0.443.
So we repeat the same process for 6 degrees, where we do +6 for the upper surface, -6 for the lower. For 9 degrees and 15 degrees. And all of these data sheets are available for you to download, as I'm sure you've already found.
So once you've calculated the data for CN and CM at the various angles of attack that we asked for 0, 3, 6, 9, and 15, go ahead and fill out this table. We are providing data for 12, 18, 21, 25, and 30 degrees. So welcome to the third part of the lab where we'll be doing some flow visualization. So here we're going to be doing smoke wire visualization. So here you can see a wire that we run a current through. Attached to this wire you can see tubing. Through that tubing we actually pump model train oil through, and that oil will create droplets that fall onto the wire. With the current running through it, it causes the model train oil to actually vaporize and create smoke, which creates a smoke sheet, which we use to visualize the flow. So this flow is actually running at lower speeds for clearer visualization, and let's get started. All right, so we're starting with an airfoil set at an angle of attack of an angle of attack of 3 degrees. So we should still be in the attached flow regime here. And so you can see that the flow is fully attached still at 3 degrees. If you look at the streamlines, we'll also be providing you with still images of these
Different angles. So let's move up to 9 degrees.
Yep. So now we've moved up to an angle of attack of 9 degrees. So now we're in the partial stall regime. And if you look at the streamlines, you can see that they're no longer attached to the airfoil all the way to the trailing edge. You can see that it's the separation point has moved up closer towards the leading edge, but hasn't reached the leading edge quite just yet.
It's separating about a quarter or a third of the way down. Stall us, baby.
So we bumped the angle of attack of the airfoil up to 15 degrees now, and now you can see we're in the full stall regime. So now you can see the separation point has fully moved up to the leading edge. You can see that there's clear separation at the leading edge now. And so now we're in the full stall regime where increasing the angle of attack does not lead to an increase in lift anymore, just an increase in drag. And now we've bumped the angle of attack up close to 90 degrees. So this is our flat plate regime. So you can see the shape of the airfoil no longer matters. What the flow sees is essentially just a flat plate. Doesn't matter that it's a NACA 0012 anymore. And so in this regime, we obviously have very extreme drags because of the conditions. So now we've replaced the airfoil with the Ferrari, very expensive car. And now we can see why it's such an expensive car. You can see it's a very streamlined object. That's why it can go so fast. You can see if you follow the streamlines, it stays attached to the body pretty much the entire way. So you're not creating any stall or anything like that, increasing the drag.
So you can go fast.
Yeah, Ferrari go fast. In contrast, now we have a truck. You can see that the truck, for the shape of the truck, it's no longer fully attached all the way through, increasing the drag. So looking at this, we can see why trucks are slow, Ferraris are fast.
Go Ferrari.
All right, so now we put in a dinosaur. If we look at the head of the dinosaur, you can see that it's actually fairly streamlined. The streamlines actually stay attached, so you'd expect it to be pretty fast, but if you look at the body, it's not so streamlined. You can see there's a lot of separation, a lot of stall around the body. So dinosaur, probably not as fast as Ferrari, maybe faster than truck, unclear.
Any other?
Similar to the dinosaur, the horse has a very streamlined head. It looks like the body might be slightly more streamlined than the dinosaur as well. So we had to guess based off of the aerodynamics, a horse is probably faster than a dinosaur.
Alright, so now we have a delta wing in our wind tunnel, and we can see two counter-rotating vortices forming off the apex of the delta wing. And we're going to take you to the back of the wind tunnel now, where you can actually see these vortices forming in 3D. And now we can see the vortices forming off the back here.
So now we're going to go over the plots you're expected to have made by the time we meet for tutorial next week. The first 5 plots are plots of the pressure distribution of the NACA 0012 airfoil at different angles of attack. Please note that the y-axis will be minus CP to follow convention for plotting airfoil pressure distributions. For the first plot, at an angle of attack of 0 degrees, you will compare your data to the pressures calculated from potential theory. As Sarah mentioned earlier in the video, you can calculate the potential curve by referring to the data provided in the appendix, which is taken from theory of wing sections. The next 4 plots are the pressure distributions of the top and bottom surfaces of the airfoil at angles of attack of 3, 6, 9, and 15 degrees. Make sure to have a spline curve that goes through your data points for each of these plots. Also, to more easily compare the pressure distributions as the angle of attack changes, make sure the y-axis for all 5 of these plots have the same scale and limits. In the lab handout, we provide a table for CM and CN values, some of which we give you and some of which you have to calculate and fill into the table yourself. We're asking that you expand upon that table and include columns for CL, CD, and center of pressure locations. The final page of your lab handout goes over the final 4 plots to be made for tutorial. The first one is a plot of your lift coefficient versus angle of attack. You will plot CL obtained from both the force balance and the pressure measurements. Compare these to the theoretical lift coefficient derived from potential theory, which is found to be 2 pi alpha. The second plot compares the drag coefficient versus angle of attack found from the force balance and the pressure measurements. The third plot shows the center of pressure versus angle of attack. For this plot, we asked you to include 2 horizontal dashed lines. The first dashed line should be at CP equals to 0.25, the quarter chord point of the airfoil. This dashed line represents the theoretical center of pressure determined from potential flow. The second dashed line should be at CP equals to 0.5, the half chord points. This dashed line represents what the center pressure asymptotes to for a flat plate, approaching an angle of attack of 90 degrees. The limits of the y-axis should be 0 and 1 to represent the leading edge and trailing edge of the airfoil. The final plot is similar to the first CL plot, but instead of comparing to the theoretical lift from potential theory, you will be comparing it to empirically obtained lift of a flat plate data, which is found to be 1.2 times sine of 2 alpha. For all 4 of these plots, you will have vertical dashed lines and labels to indicate transitions in regime from attached flow to partial stall to full stall, and finally to the flat plate regime.